All right, so welcome to our second to last class in Trig, believe it or not. Right, so we've got today, next week we have an exam, and then one more day of class, and then a final. So we're pretty much there. But my plan today is to wrap up the last little bit on polar or on complex numbers with polar form. I just want to show you how going into polar form makes finding roots a lot easier, like square roots and cube roots and things like that. And then after that, I'm going to introduce you to these things called parametric equations, which are yet another way of looking at the world that can be really, really handy and useful. All right, so that's my goal. But as always, let me start with you. Any questions on the homework or anything we've been talking about that you want to discuss real quick? All right, well, I'm not hearing anything and I'm not seeing anything. So I'm going to go ahead and jump up to the whiteboard and I'll be right back with you. All right, so last time we were looking at complex numbers. And we saw that complex numbers, if we wanted to graph them, we had to graph them in the plane. We call it the complex plane, where the horizontal axis was a real number line. The vertical axis was an imaginary number line. But to get our complex numbers, we just, went over to the real part, up or down to the complex part, or sorry, imaginary part, and then that gave us our point. But I also showed you that instead, we can think of it as a point in polar. So we talked about the absolute value, so the distance away from the origin or the pole in polar coordinates, and then going out in whatever direction, and that direction we called it the argument. So that meant we could write our complex numbers like this. So if you look at Z1, R1 is its absolute value. Its technical name is the modulus, right? That's absolute value. And then the theta ones were the angle where we were going, so the argument. And we just wrote it in this form. And where that came from was exactly the polar conversions. X equals r cosine theta and y equals r sine theta. It's just now the x and the y were the real and imaginary pieces separately. And I kind of suggested that the reason we like this is to do operations. And so last time I showed you multiplication, division, and exponents. And we saw how quickly it was, quickly we could do these computations if we were already in this polar form. And it's actually pretty easy, right? With multiplication, we just multiplied the absolute values and added the angles. With division, we divided the absolute values and subtracted the angles. And then if we took something to a power, we took that absolute value and raised it to the power, and then just multiplied the angle by n. So it's basically, we did repeated multiplication on the absolute value and repeated addition on the angle, and it led to that form. All right, so what I want to show you, just to kind of wrap this up, is what we do when we take roots. All right, and so what this is asking, for example, is like, what is the fourth root of I? What's the fourth root of I? That means what number, what complex number, if I take it and multiply it to itself, right? So I've got 4 of them being multiplied together. What number, when I do that, ends up just giving me I, right? I mean, that's what roots mean. We're kind of used to that, I think, with real numbers, right? Like if I ask you the square root of 16, and you go, oh, that's 4. Because 4 times 4 is 16, right? So we're always looking for that number that we square, cube, raise to the 4th power, whatever. It gives us what's inside. So it's no different if it's complex numbers. It just seems different, and it seems more difficult, but it really isn't, especially if we're in complex form, or sorry, in polar form. Now, let me show you how nice this is. Radicals, if you recall, radicals are the same as fractional exponents, right? Like when we write square root of x, it's the same as saying x to the 1/2. Cube root of y is y to the 1/3, and so on. And so if we do this with polar form, we're really raising to a fractional power, which means we get to use the one that's directly above it to get our radical. So instead of raising to the nth power, we're going to raise to the 1/nth power. So we're going to take the nth root. And now instead of multiplying by n, we're going to divide by n. But you'll notice I'm leaving a little space because there is something we're going to have to take care of. And I'll address that in a second. But it's kind of nice that it's just an extension of raising to a power. Roots are the same as going to a fractional power. Okay, well, clearly I'm setting us up for something because I've got some blank spaces right here. Let me address that really quickly. And let me actually start by, let's get away from the 4th root of I because you guys are probably already glassy-eyed or whatever. But what if I said, okay, find the square roots of 25. All right, so in essence, I'm just asking you to tell me a number that when it's squared gives me 25. So give me a number. Give me a number that when you square it gets 25.
5.
All right, awesome. How about 5? Is that the only one?
5i.
Okay. If you square that, you get negative 25. You're way overthinking it.
Negative 5.
How about negative 5? Right, there actually are 2 square roots of 25. 5 and negative 25. Now, when you learn square roots and when we actually use them, we only use the positive, but that's only because mathematicians wanted square root to be a function. We just wanted that to be a function so that we always got just one answer out of it. And so we just go with the positive. We call that the principal root. Well, I said the square root of 25, 5, but technically there's the second square root, and it's negative 5. Okay, so here's the deal. There are more than one root. So when you talk about a square root or a cube root or a 4th root or 5th root or any of them, there's more than one answer. I know you guys are used to just going, no, there's the square root of 25 is 5. That's because we trained you to think like functions and give just the one answer. But if we want to be complete, we got to find all of them. Okay, well, that's why we're going to need to put something in here to allow us to find all of the roots. If we just did theta divided by n, that's going to give us one of the roots. We got to find the other ones. So what we're going to put in here with this theta is we're going to put plus 2 pi k. Now, you're really used to adding a 2 pi n. Well, that's what I'm doing here. I just can't use the letter n because I'm using it for something else. All right. So when I say that plus 2 pi k, that's just finding me another angle that's coterminal to theta. Because that angle also represents the same complex number. whether I add 2 pi or 4 pi or 6 pi or 8 pi or 100 pi, right? As long as I'm adding some multiple of 2 pi, I'm going to be at the same place, which means I'm going to have the same complex number. Okay, so, and then we need to do that in the other angle as well, because those angles are the same. And what we're going to do is we're going to keep increasing k. We're going to start with 0, then we're going to go to 1, then we're going to go to 2, and then we're going to go to 3, and so on, until we get enough roots. All right, so k is equal to 0, 1, 2, and so on. And as far as we're going to have to go is actually n minus 1. So whatever index our root is, we're always going to go 1 less. And the reason that we do that is because it turns out that there are n nth roots. And this actually comes from a theorem. It's called the fundamental theorem of algebra. Don't worry about that. That's just me wanting to sound smart. So it just, if you're going to take a square root, there are 2 square roots, 5 and minus 5. If you're going to take a cube root, there are actually 3 cube roots. Take a 4th root, there are 4 of them. 5th root, there are 5 of them, and so on. So you always know how many roots you need. And so to get that many, since we're starting our count with 0, we actually only have to go to 1 under what our root was. All right, so I know it's like with all that explanation, it probably seems really confusing. You're going to see it's really easy. It's really easy. We're just going to keep adding 2 pi until we get to the point where we're not seeing the same numbers again. So let's actually look at the square root of 25, but we're going to look at it in the context of complex numbers. All right. So we're not going to think of it as just, we already know the answers are plus or minus 5. But let's find these using complex numbers. All right, so we're going to start by getting 25 in the polar form. So think about where 25 is on our graph. Remember that this is the real axis and this is the imaginary axis. And so 25 is somewhere over here because it's a real number. So let's write it in its polar form. Its polar form is going to be 25, because that's its absolute value, times cosine of 0 plus I sine of 0. And those get a 0 because that's the angle where we're going. All right, so here's what we're going to do to get our square roots of 25. Right? The square root of 25, so the square of z, is going to be the square root of 25 times cosine of 0 plus, or 0 divided by 2, plus I sine of 0 divided by 2. And this is going to be the first of those roots. All right, well, let's see what that gives us. Square root of 25 is 5. Cosine of 0, of course, is 1. Sine of 0 is 0. And that gives us 5. Yeah, I know. We already knew the square root of 25 is 5. But trust me, when we get to more complicated numbers in there, complex values, we're going to want to be able to do this process. So here was the first root, but there's another one. And the way we're going to find that is by adding 2 pi to our angle. So the other root is going to be the square root of 25 times the cosine of 2 pi divided by 2. And then I sine of 2 pi divided by 2. So I just added 2 pi to my angle. I went from 0 to 2 pi. But now I'm going to repeat the process. All right, well, the square root of 25 is 5. We now have the cosine of pi. That's -1. I times the sine of pi. Well, sine of pi is 0. And that gives us -5. So this process is going to find all of our roots. This one was really easy. We already knew that the roots were 5 and -5, but we were able to find them pretty quickly. Now, if you just kept going, you plug another 2 pi in. So we go to 4 pi. You divide by 2, you're going to end up getting this first root again. So you don't have to do more than the number of roots as the index of our radical. Right, so pay attention to your index because that's going to let you know when to stop. All right, now this one you probably feel cheated on, right? You're like, whatever, we already knew those. So let's go to one that's a little bit more complicated, one that's not quite as obvious, but is still one that you know one of the roots for. Let's go to a cube root. So this time, what I want to do is I want to find the cube roots of -8. So I know it's weird. Writing this S is really weird, right? You're used to saying, what's the cube root of 8? Or cube root of -8. You're not used to saying, what are the cube roots of 8? Or sorry, -8. But in this case, there are going to be 3 of them. There are 3 numbers that when we cube them, give us -8. Now, one of them you should probably be able to tell me. Can you think of a number?
It's -2.
Yeah, how about -2? Thanks, Jeff. So -2, if we cube that, gives us -8. That's the one that you know. So we know one of them is going to be -2. But the question is, what are the others? All right, well, let's do the same thing that we just did, which is begin by creating the polar form for this number. So -8 is going to be on the real number line, but over this direction. And so if we write that in polar, this is what it's going to be. The absolute value is 8. And the angle that points in the direction where we're going is pi. So we're going to have cosine of pi plus I sine of pi. So there it is in polar form. All right, so now we're going to go and find the 3 roots. So I'm going to go ahead and label them. So we'll start with root number 1. So I'm just going to call it R1. It's going to be the cube root of 8 times cosine of pi over 3 plus I sine of pi over 3. So all I'm doing is I'm taking the cube root of this, and then I'm dividing my angle by 3 because it's a cube root. So root number 2 It's also going to be the cube root of 8. But now this time we need to add 2 pi to our angle. So pi plus 2 pi is 3 pi. And we'll divide that by. All right, so that's going to give us our second root. And then our third root, again, cube root of 8. But now I need to add another 2 pi. Well, 3 pi plus 2 pi is 5 pi. And then we'll divide by 3. So cosine of 5 pi over 3 plus I sine of 5 pi over 3. And I'm going to stop here because, again, I know I need 3 cube roots. And here they'll be. All right, so let's find them. And this is their polar form. Let's actually get their rectangular form so that we can see what they look like. But this is just a matter of calculating these sines and cosines. So the cube root of 8 is 2. The cosine of pi over 3 is 1/2. The sine of pi over 3 is root 3 over 2. So if I take that 2 and I distribute it through, I get 1 plus the square root of 3 times I. So that complex number, 1 plus root 3i, if you cube it, you will get -8. I promise. I'll let you check that on your own. But that is one of the cube roots. Okay, so let's go to this one. Cube root of 8 is 2. And now we're going to have cosine of pi. Well, cosine of pi is -1. Plus I times the sine of pi, which in this case is 0. All right, well, that one gives us -2. Hey, that's the one we already knew about. But it's on our list. All right, well, then we get the third one in a similar manner. Cosine of 5 pi over 3. That's another positive 1/2. And then the sine of 5 pi over 3, that's actually a negative root 3 over 2. And so if I distribute again, I'm going to get 1 minus square root of 3 times pi. All right, so there you go. There are the 3 cube roots of -8. Now, when we first taught you cube roots, whenever that was, go back in time when you first learned like roots and cube roots, you were always told that there was just the one answer, it was -2. We hid the truth from you just because it's too much. When you're first learning roots, bad enough having to learn the cube root of -8 as -2. If we started throwing this I business in there, you would have no clue. So we're really just kind of filling in these missing pieces in the story of radicals. All right, but you need trig to be able to do it. All right, so there's an example with cube roots. So let's do one more. And this time we're going to make it so we're finding the roots of a number that's not at all nice, where you're not going to know any of the answers right away. All right. But before I go there, any questions on how I'm doing this? Every time I just add 2 to pi to my angle and then divide. Add another 2 pi and then divide. Add another 2 pi and divide. Just keep going until I get them all. All right, so let's do one more. This time, let's find the 4th roots of I. So since it's 4th roots, they're going to be 4. So just like here, we're going to have R1, R2, R3, and then R4. Okay. We're going to find 4 different roots. But let's start by getting the complex form, or in the polar form of that complex number. So again, let's just visualize where this is. I is going to be located up here. So in terms of its polar form, this is going to be z equals 1 times the cosine of pi over 2 plus I sine of pi over 2. Its absolute value is 1. Its distance away from the origin is 1. That's that. And then we're going in the direction of pi over 2. All right, so here we go. Let's get our 4 roots. So we're going to get the 4th root of 1 times the cosine of pi over 2 divided by 4. Plus I times the sine of pi over 2 divided by 4. So we'll simplify that in a second, but let's get the other r's. So again, we're going to get the 4th root of 1. But now we're going to get the cosine of 5 pi over 2 divided by 4. And I times the sine of 5 pi over 2 divided by 4. So all I did was I took pi over 2 and I added 2 pi. So I have 4 halves. All right, well, keep going. R3, 4th root of 1 times the cosine of, now it's going to be 9 pi over 2 divided by 4. Because I just added another 2 pi to the 5 halves pi. And then my last one, I add another 2 pi yet again. That's going to give me cosine of 13 pi over 2 over 4 plus I sine of 13 pi over 2 over 4. So add 2 pi, then divide by n. Add 2 pi, then divide by n, and just keep going. All right, so these 4th roots of 1, those are all just 1s. So this is going to give me cosine of pi over 8 plus I sine of pi over 8. The next one's going to be cosine of 5 pi over 8 plus I sine of pi over 8. Sorry, 5 pi over 8. The third one, well, now it's 9 pi over 8. And the last one is going to be 13 pi over 8. Now, these are not nice angles. Those are not on our chart. We could get them if we use the half angle identities, because pi over 8 is half of pi over 4. But I'm not going to bother with that right now, because if we wanted to know what those actual values were, we could use our technology to get there. But right now, I'm not too concerned with that. I just wanted to show you where those 4 roots are. So here are the 4 roots. There you go. Now, I know that this feels a little anticlimactic because you want to have just numbers, but they're there. They really are. But this is what I actually want to show you. Take a look at this. Look at where these things are on the complex plane. Okay, so we got those 4 roots. Let's look on the complex plane where they are. All right, so pi over 8, that's down here somewhere. 9 pi or 5 pi over 8, that's up here. 9 pi over 8 is down in the third quadrant. And then 13 pi over 8 is here. And they're all going to be distance 1 away. Remember out front, the R value, the absolute value was 1. So I don't know, let's just say that this is a distance 1. All right, so there are the 4 roots. Here was root 1, root 2, root 3, and root 4. But here's what I want you to notice from this graph. Those roots split the circle up into 4 equal pieces. Right? You do a 1/4 of a rotation to get to each of the next roots. You see the same thing with cube roots. They divide them up into 3 even chunks. 5th roots split the circle into 5 pieces, 6 roots into 6, and so on. So there's actually some really beautiful symmetry, and I know mathematicians like to overuse the word beautiful, but I think this actually is beautiful, beautiful symmetry in the roots of numbers when you allow for complex values. Anyway, take it for what it is. Like I said, we're just sort of filling in some gaps that you didn't know existed regarding roots. But there are a lot more roots out there than you know of or knew of. Now you know that they're there. All right, so any questions on this before we kind of hop to our next topic? It's just another use of trig that has nothing to do with triangles. I don't know if you've been keeping count, but in this entire quarter, yeah, in terms of how much we've actually used trig for triangles, 10%, 5%. Trig is so much deeper. It's just not. All right, so there you go. Trig form of complex numbers. Something that you thought you might never have to see again. Complex numbers come back and then get trig. Yeah, of course. All right. So the next topic that we're going to go into are these things that we call parametric equations. And to sort of set the table here, I have this question to ask you. Suppose that we have an object that's traveling on this path. All right, so this is just a path, and we've got something on it that is moving. And let's just say that it's moving in a counterclockwise direction. Okay, so got this going on. Now, we're going to have another path that does this. And there's also going to be a particle that's on this path. So let's say that it's over here. And let's say it's moving left or right. Okay, so we got the green particle, we got the blue particle. Just those 2 objects, they're moving on these paths. So here's my question. Are those 2 things going to collide? Are they going to hit each other? What do you think? Yes? No?
They could collide.
All right.
Yeah.
That's definitely true. There is the possibility that they could collide. Will they necessarily run into each other? Well, the answer to that one is not necessarily, right? So like Daniel said, they could run into each other, but it doesn't mean that they necessarily will, because even though their paths cross, like what if this pink one reaches this point on the circle while the green one is still somewhere up here? That's not a problem, right? Or if the green one goes around so fast that it gets past this before the pink gets there. So for something like this, it's not just enough to know that their paths intersect. We also need to know when they're at those points on their path. Right? Think of this as the Earth going around in orbit around the sun, and this pink thing is a comet or an asteroid. There are lots of things out there, objects out there in space, whose paths cross our orbit that we never even get close to because they're passing through our orbit at a time when we're not there. Okay, well, that's what parametric equations allow us to do. They actually allow us to describe locations in terms of another quantity. Like in this case, we can talk about their location with respect to time, right? And it's not always time, but there's just something else that's playing a role in the path, right? So it's not just the path itself, but how we travel the path. That's what leads to parametrics, right? So basically what we're going to do here with parametric equations, we're going to have x and y. They're going to be defined in terms of another variable. All right, and I'm going to put here in parentheses that it's usually t, but not always. It can take on any kind of value, but we primarily go to t because these are used in the sciences, and in the sciences, it's almost always we care how things are changing with time. But you can imagine if something's changing with temperature, okay, well, we'll use temperature, or it's changing with angle, okay, or it's changing with velocity or whatever. If we've got some other variable, we're going to define x and y in terms of it. That's what we call parametric equation. So this other variable, the name of this other variable, we call this a parameter. Hence the name parametric equations. All right, so these are equations that are in terms of a parameter. So let me just show you what they look like. They're really quite easy. The generic are going to be x equals f of t and y equals g of t. So you're just going to have x equals something and then y equals something else. All right, so let me show you some specifics. So we could have, for example, x equals t minus 1 and y equals t squared. That, my friends, is a set of parametric equations that describes a path through space, and not just a path, but a path where we know when we're at specific locations. All right, here's another one. We could have, say, x equals sine of t, y equals cosine of t. Okay, so there's another set of parametric equations that's going to define a different path, and our particle or object is going to be moving in a certain way. And I'm going to apologize, just I always will say particle moving because it's my physics brain, right? In physics, we use parametric equations primarily for particles traveling on paths. So I'm going to say that all the time, but I don't want you to think that that's the only time you use parametrics. So I don't want you to think, oh, I'm not going to be a physicist, so this doesn't matter to me. No, it's habit. Okay, so this is what we're looking at. Plain and simple. These are parametric equations. Okay, well, let me show you how these work in terms of getting the graphs. So suppose we just want to draw a graph of this one, this first one, where x is equal to t minus 1 and y is equal to t squared. Well, it is going to be a whole bunch of points on our graph here. But in order to figure out what points they are, I'm going to do what we did before when we wanted to draw graphs, which is just plug in numbers. You remember the t-chart, right? Except now it's not a t-chart. It's like a double t-chart, where we're going to plug in values for t, and we're going to use those to get values for x and y. All right, so we'll just do 5 values here because this should be sufficient for us to figure out what's going on. So let's just do the values from -2 to 2. So all we're going to do is just plug them in. So at -2, x is going to equal -2 minus 1, which is -3. And then y is going to be -2 squared, which is 4. So that means that there is a point on my graph at -3, 4. Well, that's this guy right here. And I'm going to go ahead and just put t equals -2 with an arrow, just to remind us where that one came from. That came from t equals -2. All right, so plug in -1. -1 minus 1 is -2. -1 squared is 1. Okay, so there's a point over here at -2, 1, and that corresponded to t equals -1. All right, well, let's just keep going. If I plug in 0, I get -1 for my x and 0 for my y. That's right there. When I plug in 1, I get 0 for my x and 1 for my y. And then when I plug in 2, I get 1 for my x and 4 for my y. And I don't know if you can tell, but if we start kind of piecing this together, we're starting to see a parabola. So this actually defines a parabola, defines this parabola, but even more, it doesn't just show a parabola, it shows us how we're traveling on that parabola. At t equals -2, we're at this point. At -1, we're here. At 0, we're there. Then 1, and then 2. So there's an orientation to this graph. There's a direction to it. So I'm going to put some little pink arrows on here to show you the direction that we're traveling this path. And that's the strength of parametric equations. If I didn't care about that orientation, I could have just given you the equation for this thing, the y equals. But by using this parameter t, it's now telling us not only what path we're traveling, but how we're traveling that path. So speaking of, what is that path? Do you think you could get the equation of that parabola? And I know what you're thinking. Oh, good Lord, I don't remember anything about parabolas. Something about a vertex. And well, check this out. You can actually get the equation really easily by doing what we call eliminating the parameter. Eliminating the parameter is exactly what it sounds like. We're going to get rid of the t. And the way you do that Well, in the case of this first one, is we could solve that first equation for t. All right, take this x equals t minus 1. If we solve it for t, we get t is equal to x plus 1. And then we can take that x plus 1 and we can replace it into the other equation for y. So this would give us y equals x plus 1 squared. And if you remember your transformations, you can see how this is this parabola. It's just the good old happy parabola. It's a good old smile that shifted 1 to the left. And you can see that here. So take that parabola and just shift it over 1. So this is a really handy thing to do if you want to know what your set of parametric equations actually looks like what the path looks like. You can eliminate the parameter, but remember that if you do this, you lose everything about how it's traveling on that curve, right? If I just said draw the graph of y equals x plus 1 squared, you draw this parabola, you wouldn't know that the particle is going from left to right. I mean, you wouldn't know anything about it. So you lose information when you eliminate the parameter. But it makes it so that you can actually, well, I don't know, draw the graph of it. So if you want to eliminate the parameter, and I actually do recommend that a lot, just to, especially when you're new to this and you're trying to figure out what the shapes are and what they're doing, eliminate the parameter, because you get back to rectangular, a lot of times you know exactly what it looks like. Then you can go back and look at these things specifically and see what's going on with the x's and the y. All right, well, let's try that with this one. The x equals sine t and the y equals cosine t. Let's eliminate the parameter. Let's see if we can figure out what the graph looks like instead of doing the t chart. But we could do the t chart, right? We could plug in different t values, get out different x's and y's and kind of plot the points. But let's see if we can do it just by eliminating the parameter. So I'm going to bring that over here to get it a little bit out of the glare. So let's look at this one. So we're going to eliminate the parameter for x equals sine of t and y equals cosine of t. All right, so if we're going to do it the same kind of way we did right here, we want to solve one of the equations for t and then plug it into the other one. So let's go ahead and do that. Let's start with the x equals sine of t, and let's solve it for t. What do you have to do to get t all by itself here?
Take the inverse sine of x.
Beautiful. So we have the inverse sine of x is equal to t. Right? Inverse sine brings us up. So then we're going to plug that into our y. So we'll take this inverse sine and we'll put it in there. So we get y equals cosine of inverse sine of x. All right, so does that help you? Anybody recognize that graph? And you can tell from my shit-eating grin that I don't expect that that helped at all. Right? Cosine of sine inverse of x. What the hell is that? Well, let me transport you back in time. I think this would have been probably in May, maybe the earlier part of May. This is that mixed composition with the inverse trig functions. And this is the one that we can actually get, we can eliminate the trig bits if we use identities or draw the right triangle? I suggest we draw the right triangle. So here's what we know about this. We know that the sine of theta is equal to x. So in the triangle, I think sine is opposite over adjacent, or sorry, over hypotenuse. That's x over 1. Right? I need to get this third side. I can use the Pythagorean theorem for it. And that's going to give me the square root of 1 minus x squared. I'll let you check that on your own. But now what I need is the cosine of that angle. Well, that's the adjacent over the hypotenuse. So this actually now looks like y equals the square root of 1 minus x squared. So we're able to actually get rid of the inverse trig. Now, I don't know if that helped you at all. Anybody recognize this one? You might recognize that. No? All right, well, let me help you one step further. Let's square both sides. If we square both sides, we get y squared equals 1 minus x squared.
Isn't it a hyperbola or something?
Oh, nice. Now we're getting close. I like how you're thinking of hyperbola because you saw the positive and the negative, I'm betting, right, Joe?
Oh, it's a circle, yeah, because you move it over. Never mind, yeah, it's a circle.
We move it over, we get x squared plus y squared equals 1, which is a circle of radius 1, centered at the origin. So this parametric set actually gives us a circle, or at least part of the circle. We're not going to actually know how we're traversing this until we plug in t values and see what's going on. But I do know that that path, pretend that that's a circle, it's actually the unit circle. So this set of parametric equations is going to give us the unit circle, or at least part of the unit circle. But the question is, which way are we traveling around this thing? Well, this is where now we could actually plug in some t's and see what's going on. So think about it, t equals 0. We're going to get x equals 0 and y equals 1. So that means we're actually up here at t equals 0. Let's go to pi over 2. That's the next really nice number. At pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0. So we're actually at 1, 0, which is over here. So we went from the top down in this direction. And if you continue doing this, plugging in more t's, you're going to see that what we're doing is actually traveling around this circle in a clockwise direction. So it's not our usual counterclockwise, but we're going in a clockwise direction. And we actually started at the top. All right, well, I mean, that's just how we write that set of parametric equations. But this also kind of illustrates the power of parametrics, is we can take something that we know really well and now travel it in a different way. And that's kind of nice to have. Let me show you a faster way we could have gotten to this x squared plus y squared equals 1. Because this was a pain in the ass, right? I think we can all agree that when we get these and we have to do the whole right triangle business, it's kind of complicated. Well, we could have used the trig identities. Remember Pythagorean? Sine squared plus cosine squared equals 1. Well, sine, that was x. Cosine, that was y. Yeah, there you go. X squared plus y squared equals 1. Don't forget your identities. They come in really handy at random weird places. All right, so this is the idea behind parametrics. It really is, we're just going to now describe where we are as we're traveling the path. So you can take parametric equations and eliminate the parameter. So you get to a good rectangular form. And you can actually do go the other direction. Given a function or an equation in rectangular, you can always make a parametric set for it. So let me show you how we can go the other direction with these. And then I'm going to hop onto the computer and show you how you can use technology to help you graph them. But let's do this first. Let's find a set of parametric equations. For the curve y equals let's stay pretty easy. Let's go with 3x minus 4. So you guys all know what that looks like. He says confidently. It's a line. Slope of 3, y-intercept of -4. Right. All right, so it's a line, but let's create a set of parametric equations. So that means we need to have x equals and y equals. And we need those both to be in terms of t. Now I'm going to give you a little secret here. I'm going to tell you a secret. This is the easiest thing to do in the world. It looks like it's going to be a complicated, like I just wrote this and you went, oh my God. You want to see how easy it is? Tell me a function for x in terms of t. What do you want x to equal? Anything you want.
1.
Okay, but it needs to have t's in it. How about 1t? That'll work for you? Okay, so let's just say we let x equal t. All right, so now we got to know what y equals. Well, all you got to do is substitute this, what we just chose for t, in here. And so we're going to get y is equal to 3t minus 4. So guess what? You just parameterize that curve. All you got to do, if you want, like, if all you need is a parameterization, let x equal t. But we could have chosen anything, right? So there was one of them. I'm going to put a big 4, because here's another parameterization for this curve. How about we do y or x equals negative t squared. Okay, so now I'm just making stuff up. But I'm going to do the same thing. I'm going to plug this in for x. So that means y is going to be minus 3t squared minus 4. Okay. Or let me give you one more. What if I let y equal, or sorry, x equal e to the t? Why not? X equals e to the t, then y is going to equal 3 e to the t minus 4. Or. Okay. If you want to parameterize the curve, all you got to do is pick something for your x. Then plug that in for x, and you can get your y value. But I will tell you that depending upon which of these you pick, you might actually get different parts of the graph. You're definitely going to get different direction, different types of travel on the graph. And let me show you that with a couple of examples here. We'll start with the first one. Think about the x equals t, y equals 3t minus 4. So I'm going to start by just drawing the graph of 3x minus 4, because we know what that looks like. So we've got an intercept at minus 4. It's got a slope of 3, up 3 over 1, up 3 over 1. So pretend that that's our line, that that's a line, but that's the line that we're looking at. All right, so let's see how we travel this with some of these different forms. So if we think this one, where x is equal to t, at t equals 0, we're right here. At t equal 1, we're at that next dot. T equal 2, we're at this point. So I'm going to put little red arrows showing the direction of travel for the red one. So x is equal to t and y equals t minus 4. I traverse this path and I get the entirety of the graph. Because x is equal to t, if the t's can take on all kinds of values, x is going to take on all those, so I get the entire thing. All right, now let's look at this orange one. Now, what I want you to notice, first of all, notice with the x is always going to be negative. Because t squared is positive always. And so we're slapping on a negative on there. So this one's kind of funky. Like if we're at t equals 0, we're actually at the same point. We're right here. But if we go to t equals 1, our x is going to be negative 1, and our y is going to be negative 7. When I go to t equals 2, I'm at negative 2, or sorry, negative 4. That's way down here. All right, so think about this with the orange. I'm going t equals 0 to t equal 1 to t equal 2. So it appears that I'm going this direction, right? Well, if I plug in negative 1, I actually get the same spot as t equal 1. And the same thing if I plug in negative 2, I get the same as positive 2. So if we were to describe the path from the orange, here's what it does. I'm going to redraw it kind of over here. It's going to go up on our graph and then come right back down. But it's going to stop at the axis. So this second one doesn't actually give us the entire line. It only gives us this part that's to the left of the vertical axis. So this is just something you have to be careful about when you parameterize, is that it's possible if you pick something that you don't get the entirety of your graph. And I only bring this up, not so much for this class, because this class we're just kind of learning about them. But If you end up using this in science, depending upon where you're going, if you're going into the engineering physics stuff, you're going to use parametric equations. Then you have to be really careful that you're actually getting what you want, right? That you're getting the part of the graph that you want to see. All right, so just be careful with how you parameterize. But in general, all you got to do is pick your favorite thing for X and then plug that in for Y. All right, so those are parametric equations. It's really just now we're describing the path and how we're moving on the path. So there's more information. That's what the parameter does, is it gives us that information. Okay, I'm going to hop back down to my computer because I want to share some things from the web, just so you can see some online resources or how you can use technology to help you look at these things. So I'm going to hop right back there, and I'll be back with you in just one moment. All right. So when it comes to graphing these things, you don't do them by hand. Okay, we don't. We never graph these by hand. And I want to show you how you can use your technology to do this. Now, if you've got a handheld calculator, a graphing calculator, they usually have a mode for graphing in parametric. You know, I've got a TI-89, but the same thing goes if you got an 84 or a TI-83 or a Casio or whatever. You know, so if you go into the different modes, you'll see one for graphing. And like mine, it says function as an option. And the next one on the list is parametric. There's also polar, there's also some other stuff, but you can always use that. And if you go into that mode, what you should see when you go to type in your graphs, instead of Y equals, it will say X equals and Y equals. Now, I only use my calculator to do this if I don't have access to the internet. Because if I've got the internet, I like to go to this place called Desmos. And I think I've shown you Desmos before. We were using that, I believe, when I did the polar plotting. So let me show you how we can tell Desmos to graph parametrics. All right, so we got Desmos up here. And when you want to just do regular graphs, remember what you can do with Desmos is just type in your Y equals. So you could do something like Y equals 3x squared minus 4. Right, so there's the graph of Y equals 3x squared minus 4. So super easy to do rectangular. I also showed you how we can do polar, and that's where we do the R equals, right? So you do something like 4 cosine of 5 theta, right? So with polar, it was just, you can type in R, and anytime you want a theta, you actually type the word theta, and it'll graph it. So there's your 5 petaled rows. Now, if you want to do parametric, you're actually going to put it in as an ordered pair. All right, so let me show you the one that was X equals sine of t, Y equals cosine of t. Okay, so I'm going to put an ordered pair where my first coordinate is sine of t, and my second coordinate is cosine of t. So this is literally X equals sine t and Y equals cosine t. Now, if you look at this graph, it doesn't look much like a circle. It's actually only part of the circle, because you'll notice that down here, it has some values for t. This is only graphing from t equals 0 to t equal 1. And so by the time we get to t equal 1, we've only gone this far on the circle. If I extend this, let me change that to a 2. And now if you look at that graph, our circle has been extended a bit. Well, let me change it to a 3, 4, 5, 6, right? And eventually, it's going to get big enough that I'll see the entirety of our circle. So if it looks like your graph is incomplete, change your t-values so that it shows you a little bit more. All right, well, let's look at the one that we just did with that line, but the one that was specifically negative t squared. That was our x. And then the y was 3, so negative 3 t squared. And then I believe it was plus 4. No, minus 4. All right, let's move this up a little bit so we can see it a little bit better. And you'll notice that this is for t equals 0 to 1. So we're only seeing this portion from 0 to 1. Now, if I extend it out, let's go to 2. And notice how it grew longer this direction. Let me really zoom out here. We'll change it to 3, and you'll see that it gets even longer, right? So it's going in this direction when it was positives. Now, let me change this so that we're doing negatives. So there's from negative 1 to 0, negative 2 to 0, negative 3 to 0. And you see that we're getting the exact same thing. And never do we get on the positive side of the axis. All right, so that's the other nice thing about using your technology is it can actually show you what part of the graph you're getting, because you don't always get the same part. Like here's another one. Let's do the same line, but this time, let's turn it off. Instead of x being equal to t, let's say x was equal to cosine of t. So then y would equal 3 cosine squared. Oops. How about I type it properly? Cosine t squared minus 4. All right, so we're seeing only part of that line, right? Is that part of that line between 0 and minus 1. So, or 0 and 1. So let me extend it. Oh, shoot, there's no cosine. Hold on. Or no squared. There we go. There we go. Let's go back to 1. So there's our 0 to 1. But if I extend it, say 0 to 2, went a little bit longer. 0 to 3, I got a little bit longer. 0 to 4, it did not get longer. 0 to 100, it did not get longer. Okay, wait a minute. So it's not getting longer anymore. Well, let's back that up a bit. But now let's go to negatives. Let's see what happens if we do negatives. Actually, go 0. So go say negative 1 to 0. All right. Negative 2 to 0, still a little longer. Negative 3 to 0, yeah. Negative 4, okay, it looks like we're about done. So check this out. There's like from minus 4 to 4, you notice it didn't change. So this one, we're only getting this portion of the graph. And what's going on with our particle, this one's pretty fun, is it just keeps bouncing back and forth like a ping pong ball, like bonk, bonk, bonk. It's just moving constantly back and forth because think about the x coordinate. Cosine goes between plus and minus 1. So our x coordinate goes to 1, then it goes to minus 1, then it goes back to 1, and then it goes back to minus 1. So that is the one thing that we lose when we graph it on something like Desmos is we don't necessarily see how it's moving. But if you look at the specific parameterization for X and Y, you can often figure out what it is. I know that I've got a graphing mode on my handheld that's it's called like animate or something like that. And it takes a little circle and it shows you how it's graphing it. And in parametric, that's really good because you can just kind of follow that circle and go, oh, it's just going backwards and forwards. And so you know how it's traversing. I'm sure that there's probably a way to program Desmos to do that. I don't know it. I'm too lazy to figure out because I've got this if I need it. But anyway. All right, so there are parametrics. It's yet another way of looking at the world and looking at curves. It's just one that gives us more information. It tells us not only the path, but how we traverse the path. All right, so we're definitely a good place for stopping in terms of new material, but we do have a little time, and I want to talk a little bit about the exam that's coming up and what to expect for the rest of this class. So on Monday, we have our final regular exam, right? So it's exam 3. It's going to cover section 9.5 through 10.5. All right. And in fact, let me go ahead and I'm going to go to the whiteboard here and write this down so everybody can see it. Let's clear all that stuff. Okay, so the exam Monday. It's for sections 9.5 through 10.5. So what that entails, 9.5, this is trig equations. So expect some questions on there about solving trig equations. A good place to go back and look at quiz, I think it was number 4, not the most recent one, but the one before, I think it was quiz number 4. That was a lot of solving trig equations. So just things to remember there. Don't forget like factoring and identities and some of those kind of tricks to help us get it so that we have just the one trig function. If you've got extra stuff inside, make sure you get your angles first, then solve for what's inside. And always make sure you add on the plus 2 pi n or plus pi n, depending upon which trig function we're using. Make sure you do that as soon as you do inverse sine, inverse cosine, inverse tangent. And also make sure you find all of the angles. And this is really an issue mostly with sine and cosine because of the fact that the period is 2 pi, but there are multiple places in that 2 pi where you'll see solutions. All right, so that was 9.1. So then 10.1 and 10.2, I'm going to kind of lump those together because these were solving the oblique triangles. So oblique, this means not right. And so really this was the law of sines and law of cosines. So know how those work, know when you need to apply one versus the other. Remember my recommendations when finding angles. If you're using the law of sines, if you have a choice, go for the smaller angle. And if you're using law of cosines, go for the bigger angle. That will help keep you from getting into those weird situations where you get the wrong angle. But there is that one case, the SSA, the two sides and the angle opposite one of them, where you always have to check your second angle from the law of sines. And so you might actually get 2 triangles in that case. And then the one other thing that was in 10.1 and 10.2 was areas as well. So just going to remind you that was area. So expect problems there on those kinds of things. So this is going to be very much like the quiz you just took. So quiz number 5. So quiz 4 and quiz 5 really cover these. So that's going to be a good place to kind of look back and see questions that are similar to what will be on the exam from those sections. Okay, so then 10.3 and 10.4, those things also lump together. And those are the polar coordinates. I think it's like 10.3 is the introduction and this is how they work. And then 10.4 is the drawing the graphs of them. So they just kind of blend together there. So the important things to remember for polar coordinates are the conversions. So we get x is equal to r cosine theta and y is equal to r sine theta. That's how you convert from polar to rectangular. And then if you want to go the other way, we have that r squared is equal to x squared plus y squared. And the tangent of theta is equal to y over x. But none of this is new. This is actually stuff we learned in week 1. Just definitions of sine and cosine and tangent and all that. But we are using them in kind of a different way. So the big things to be able to do in polar, now I know you haven't had a quiz on this, so but you've got the homeworks that you're working on right now. So it should be things like the homework, but things that are important to know how to do. Know how to convert between the forms. If I give you a polar point, be able to determine what it is in rectangular. Rectangular point, figure out how to give it to me in polar. Don't forget that there's more than one way to represent a rectangular point in polar, because we can do, angles differently with different directions, extra spins. And we can also have r be positive or negative. Just remember, if you get a negative r, it really means go the opposite direction. So be able to convert points, be able to convert equations from one form to the other, and know the basics on the graphing. If we were in person, I would give you one of these that you would have to graph by hand without your calculator. But since this is a take-home thing, I can't do that because you'll just type it into Desmos. So I'll have to think of something else to make you kind of graph it. But just remember the general idea of the graphing of them. Okay, so that was the 10.4. And then 10.5, this was the complex number stuff. And this actually kind of lumps back into polar, because that's all we're doing is we're converting them to polar. Yeah, we're just looking at the complex plane. So instead of x's and y's, we're looking at reals and imaginaries. So things to know how to do there are know how to convert the from one form to the other. So if I give you the a plus bi form, the rectangular form, turn it into polar form or vice versa. And then know how to do the computations in polar form. The multiply, the divide, the powers like we did last time, and then the radicals like we did today. All right, so that's what this last regular exam is going to look like in terms of the content. I will tell you that most people like this exam a hell of a lot better than exam 2. If you remember exam 2, if it's still in there, because a lot of us have blocked it out already, that was the one that was like super identity heavy, and and the graphs of sine and cosine and all that, and so that's pretty challenging. Now we're applying it. Most people like the application. So hopefully exam 3 goes a little bit better than exam 2 for you. If exam 2 was rough, this one should be not as rough, hopefully. But anyway, so that's what this exam is going to look like. Don't forget to work on your homeworks. I know that the next set of homeworks that are due cover the last couple sections here in chapter 10. So don't wait until Monday night to do those. Use those to help you study as well along the way for the exam on Monday. Okay, so that's what's going to happen on Monday. So then on Wednesday, we're going to talk about vectors. And this is the last section of the book, of the chapter on trig applications. So I think it's 10.7. I'm going to put a little question mark on that because I'm not sure. So, well, we'll also, hopefully I'll have the exams graded. If not, we'll for sure at least go over the exams off the record before we start. But then we'll talk about vectors. And then with the remaining time, we'll do a little bit of review for the final. Because that final exam, it's coming faster than you can imagine. Right? So our final exam is the following Monday, or was it Wednesday? I don't actually remember. Hold on. Let me find it real quick. unless anybody has the syllabus handy and can tell me. It's a race. Oh, I'm so close. It's on the 21st, which is the Monday. Yeah. All right. So we're going to be done like sooner than you can think. I mean, it's pretty crazy how fast this is coming. So I want to get back to where I am. So then, and vectors is actually 10.8. Okay, so then the final exam is going to be on Monday, the 21st, 10 a.m. with a 1 p.m. deadline. All right, and this is going to be the final exam. And the final exam is cumulative, meaning everything from this quarter is fair game. But to be honest, we're still using stuff from the very beginning of the quarter. So luckily, trig is one of those things that really builds on itself. So it's not like all of a sudden there's this random thing that we have to go back to. So and just be aware that that's going to be cumulative. Now, I do want to just talk for a second about exams and like uploading. There are still many of you that only email me these files. It is so much more difficult for me when that happens. I really need you to upload it in Canvas. And that's why I give you all that extra time. All right. Many of you, I think a lot of you have been seeing that extra time as, oh, this is just extra time to do the quiz or the exam. No, that's not the idea. So like think about this exam on Monday that starts at 11 and has a due submission time at 1:30. The idea is for you to be done with that test by 1. So start working on uploading it, converting it to a PDF, all that kind of stuff, but convert it through the assignment page on Canvas, please. Don't push the time, right? It's when you guys are starting, oh shit, I got 2 more minutes and you're trying to upload and then it's like, I get the email, oh, it wouldn't let me upload it. And my response in my head is always, yeah, because you're trying to do it after it's over, right? I understand that there are technical issues. That's why I build in that extra time. Use that time for that. I'm not going to be a hard ass on exam 3, but I am going to be on the final exam. On the final exam, if it does not get uploaded through Canvas, I am not going to accept it. Okay, so you guys have had plenty of time to get it figured out. If you haven't figured it out yet, you still have a chance to get it figured out. All right. It's just, I'm getting really frustrated with it because it's like a big pain in the butt to deal with it. And then I get emails from you guys, oh, have you graded it yet? It's like, well, no, because I had to go dig through my email to find it. And, all right. So to make everybody's life better, including yours, upload it on Canvas through the assignment page. If you don't know how to do that, ask one of your peers, because most people in this class know how to do that. Most people do it, okay? So please just do me a solid, right? As we're getting here at the end. Anyway, all right, so that's what's gonna happen here the next couple of weeks, man. We're almost there, almost there. I can feel it. Anyway, so we have a little bit of time. Any questions about what to expect on the exam or anything you're not sure of?
I just have a question for the review. Is there going to be like a review packet, or should we just come with questions?
Definitely come with questions. I don't know if I'll have a review sheet packet. Sometimes sometimes I have them, sometimes I don't. Kind of depends on how I'm feeling. Part of this is going to depend on whether or not I can find it, because most of that stuff's on my computer at work, which I haven't been to in a year and change. I do have some things that I have accessible through cloud and all that. So if I have one, for sure, I will include it in the Canvas shell and get it out to you guys ahead of time. But no promises on that. If I don't, and even if I do, please come with ideas of things that you want to ask me on Wednesday. because that's a very good time to do it. All right. But in terms of office hours and everything, I'll have the same office hours for the next couple of weeks. So you'll still find me at the regular times. If those times don't work for you and you'd like to meet some other time, please let me know. I'll be more than happy to do that as well, as long as it works between our schedules. All right, well, then I think we'll go ahead and wrap this up. I'm gonna go ahead and stop the recording and just gonna wish you well. Good luck on the test. And I will see everybody on Wednesday, right? Because there's no class on Monday, it's take the test. So have an awesome couple of days, or I guess week, and I'll see you all on Wednesday.